So I'll talk about tight bounds for L1 Oblivious Subspace Embeddings. This is joint work with Ruosong Wang. So we're going to look at the LP regression problem. We're given a matrix A, which is n by d. We're going to focus on the overconstrained case, so a tall, thin matrix, a vector B and Rn, and we want to find x and Rd to minimize the p norm of Ax minus b. Okay? So we've seen a lot of talks on p equals 2, which is least squares regression. Most of this talk is going to be about p equals 1, which is least absolute deviation regression. So we're summing up the absolute values of the residuals. Yeah, as I said, overconstrained case, n is much larger than d. So what's one way of solving least squares regression? We know that the minimum norm solution, x star, is A pseudo inverse b. But calculating this could be very slow. So there are lots of ways to speed this up by sketching or by allowing randomization and approximation. So here is a technique introduced by Sarlos back in the day. So given this matrix A, you choose a random matrix S, let's say with R rows, which is wide and fat. And you say that it's an LP subspace embedding if the following properties hold. So with constant probability, so here the order of quantifiers is important. With constant probability, simultaneously for all d-dimensional vectors x, the p norm of SAX is the same as the p norm of AX up to a distortion factor kappa. Okay? This is a subspace embedding. And this gives a very simple sketch and solve paradigm for regression. So how do you solve LP regression? Well, you just compute a subspace embedding S for the matrix A concatenated with the vector B. And then you know that all solutions of the form Ax minus b have their norm preserved by S. Okay, their p norm preserved up to a kappa factor. So you get a kappa approximation by minimizing the regression problem in the sketch space. Okay, so we know a lot of subspace embeddings for the 2 norm. In particular, if we choose a number r of rows to be order d over epsilon squared, then a matrix S, the sketching matrix, with r rows, that all the entries are IID normal random variables with mean 0 and variance 1 over r, gives you a subspace embedding. And the proof of this is basically you use the Johnson-Lindenstrass lemma to show that for a fixed vector, you preserve its length with super high probability. And then you put a sufficiently fine net on the entire subspace, and you argue that you preserve all net vectors, and therefore you preserve the entire subspace. Okay, so this is all standard stuff. Note that one property about S is it's an oblivious embedding. Okay, so unlike some kinds of sampling, like leverage score sampling, it doesn't actually depend on the data set. Okay, so this isn't a very good subspace embedding computationally, because computing SA requires at least nd squared time. You can solve the problem exactly in that amount of time, so it doesn't buy you much. But there are all these improvements to speed this up. There's the whole subsampled randomized Hadamard line of work that I'm not mentioning here, but let me just mention count sketch here, which is particularly suitable for sparse matrices A. So this is work I had with Ken Clarkson, also work of Mung Mahoney and Nelson Nguyen. So what's shown here is if you choose the number of rows in your sketching matrix to be a little bit larger, like d squared over epsilon squared, then you can choose this super sparse count sketch matrix to solve L2 regression. So it just has a single non-zero entry per column chosen in a random location. And you can show that with this number of rows, with constant probability, you get a subspace embedding. Okay, so just as we've described, the number of rows is a little bit larger than the Gaussian case. I mean, d squared as opposed to d, but still independent of n. And the proof of this that it's correct uses a critical observation, so that the Johnson-Lindenstrauss and net argument that we use for Gaussian matrices does not actually hold for count sketch matrices. Count sketch matrices don't preserve an exponential number of vectors, don't preserve the length of an exponential number of vectors with good probability, but sort of the the observation here is the net that you put on this d-dimensional subspace, even though it has exponential size, the net vectors all live in a low-dimensional subspace, and this allows you to have a different kind of argument that it gives a subspace embedding. Okay, so I imagine many of you are familiar with this, and the point here is that computing S times A is very fast. Okay, so n in Z of A, number of non-zero entries of A time. And there is a lower bound on this sketching dimension. So this d squared dependence is tight for oblivious L2 subspace embeddings if you're only allowed a single non-zero entry per column. Okay, so Nelson Nguyen showed this, even just to preserve the rank. Okay, and there's a more general trade-off called the Osnap family of sketching matrices, developed by Nelson Nguyen, Bourgain, Dirksen, Nelson, and the latest is due to Cohen, which says the following. So instead of choosing just a single non-zero entry per column, suppose I choose f non-zero entries per column in uniformly random positions. Then I have the following trade-off. If S has the form log base B of D, all divided by epsilon, where B is a parameter, then I can get a number of rows B times D log D over epsilon squared. Okay, so just to instantiate this for some intuition, if B is D and epsilon is a constant, then this number of non-zeros per column is a constant. And if B is D, this is like roughly D squared. Okay, so it's count sketch on one extreme. But also note that if B is something like D to the 0.1 and epsilon is a constant, this is still a constant number of non-zeros per column. And then you get something like D to the 1.1 rows up to log over epsilon squared. And in general, if B is a constant, then you'll get like log D non-zeros per column and a number of rows, which is D log D over epsilon squared. Yeah, question?
Are the entries random size or do they need scaling? Do they need scaling?
Oh, yeah, sorry. I'm missing a scale factor, which is 1 over root S. Yeah. OK, so there's a lower bound here, which is that if you want this number of non-zero entries per column, S, then you actually need B times D over epsilon squared number of rows. Okay, so there's a gap here, but it's only a log factor. Okay.
If you choose S larger, do you need to use the entropy concentration thing, or can you use the usual net argument?
Oh, so they do this by bounding higher moments of the trace. Yeah. So I don't know if it is an argument.
That argument works, or you don't know?
I don't think it. I don't think it works. Yeah, but yeah, I'm not aware of one that works. Okay. Okay. So this talk is mostly about other norms, in particular the L1 norm. So what can we do for L1? Can we use similar constructions? So what were the ingredients for L2 for this Gaussian embedding? Well, we had the Johnson-Lindenstrauss lemma, preserve the norm of a fixed vector. And basically, all we were using there was that the Gaussian distribution is too stable, right? So inner product with a fixed vector and a Gaussian vector gives me a Gaussian times the 2 norm of that fixed vector. And then we use strong concentration of sum of squared Gaussians, and we use the net argument for the subspace. Okay, so can we follow the same recipe for L1? Okay, so the first thing we want is a kind of stability. And what is a natural random family of variables to consider? So we consider the Cauchy distribution, which is one stable. So I'm given scalars a1, a2 through an, and I scale them by independent Cauchy random variables. I add them up, and I get a new Cauchy random variable times the 1 norm of those scalars. Okay? So here's the Cauchy distribution. It's very heavy-tailed, so the density function decays like as 1 over x squared asymptotically. So these things are not very nice. The undefined mean, infinite second moment. You can at least generate them as the ratio of 2 normal random variables. The tail bound is not so good, so the probability the absolute value of a Cauchy is greater than x is roughly 1 minus 1 over x. OK, so what can we do with these? So if we try to follow this recipe that we had for L2, we have the one stability of the Cauchy distribution. Then we could try to get some kind of concentration bound on the sum of absolute values of Cauchys. Right? This would be the analog of the concentration for the sum of squares of Gaussians. And then we could hope to do a net argument for the subspace and be done. Right? The issue is the Cauchy distribution is very heavy-tailed. So there's no concentration, no good concentration here. And so this recipe doesn't really work. OK. Nevertheless, you can do something. So what we showed with Zoller is if you choose a number r of rows for your sketching matrix to be d log d, and you choose an r by n matrix of IID Cauchy random variables, then you do get a subspace embedding, but it doesn't have this nice 1 plus epsilon distortion that we were talking about earlier. Instead, what it has is the property that for all x, the one norm of SAX is at least the one norm of AX times r, the number of rows, and at most the one norm of AX times RD log D. Okay, so if I divide out by r, then this gives me subspace embedding with d log d distortion. Okay, so at least it doesn't depend on the large dimension, but it's not as good as 1 plus epsilon. So how do you prove this? Well, there are two parts. You first want to show that if you look at a vector AX, its L1 norm doesn't shrink that much when you multiply it by S. This part is easier. So this you can actually carry out this net argument and use a Cauchy lower tail inequality. So if I apply the matrix S to a fixed vector AX, what does the first entry of SAX look like? Well, by this one stability property, it's a Cauchy random variable times the one norm of AX, right? And then I look at the second entry of SAX. It's an independent Cauchy random variable times the one norm of AX. Okay, so I have R independent Cauchy random variables scaled by the one norm of AX. And if my one norm of SAX really shrinks by a lot, then it means a constant fraction of those independent random variables all had to shrink by a constant factor. But that's unlikely, right? The median of the absolute value of a Cauchy distribution is a half. The probability it shrinks to something like 1/10 is less than a constant. So with very high probability, like the failure probability being exponential in R, I'm going to have the property that the one norm of SAX is at least omega r times the one norm of AX. That's just the Chernoff bound. Is that clear, people? OK. But if I have failure probability 1 over 2 to the r, then if I set r to be d log d, that's enough to union bound over a net. OK, so I have the property that vectors don't shrink when I apply the sketching matrix S. OK. So you might ask, well, what about the upper bound? And this is problematic, right? If I take a fixed vector AX and multiply, take the dot product with a Cauchy, I'm going to get a Cauchy times the one norm of AX by stability. But the Cauchy deviates a lot, right? I mean, the Cauchy will be, it'll be like 1 with, say, probably a half. It'll be 2 with probably a fourth, 4 with probably an eighth. I mean, it's going to deviate a lot. So we can't do the same net argument. So instead, we use an Auerbach basis. This was introduced in this line of work in a paper of Dasgupta. Mike Mahoney is on that, and others. So what it says is for any d-dimensional subspace of Rn, I can find a basis U with the following properties. The one norm of each column of U is 1. And also, I mean that I get just by scaling. Also, for any vector x, the one norm of ux is at least the infinity norm of x. Okay, so this is some kind of nice structural condition which you can think of as some kind of analog of orthonormal bases for L2. I mean, it's what we have for L1. I'll say more about this later, actually. But OK, so every d-dimensional subspace has this. And given this, it's fairly quick to show the upper bound for subspace embeddings. So it only takes 2 steps. The first step is to look at S times U, where U is a special Auerbach basis for your subspace of interest. So what does S times U look like? What are the entries? So the columns of U have unit L1 norm, right? And the rows of S are IID Cauchy. So each entry of SU is just a Cauchy random variable, standard Cauchy random variable. And I have an R by D matrix of standard Cauchy random variables. There's some slight dependence between these entries. I'm not going to get into that. But what you can show is basically if I have an R by D matrix of Cauchy random variables, you expect about half of them to be about 1, about a fourth of them to be about 2, about an eighth of them to be about 8, and so on, right? They have this kind of behavior, this tail behavior. And so you can just show that, so I'll have, say, half of them being 1. That'll give me like R times D, plus a fourth of them being 2. That'll give me another R times D, and so on. So you'll get log RD scales, each one contributing RD. And you can show that the one norm of this matrix SU is about RD log RD. Yeah, question?
When you say matrix one norm, is it element-wise or induced?
Yeah, this is element-wise.
Okay.
Yeah, yeah. Any other questions about this? Yeah.
Maybe I missed it. So when you did the Auerbach basis, the second condition says that for all x?
Yes, this is a condition for all x.
What's the intuition behind this condition?
What's the intuition why you can find a basis of this form?
Why is this a natural? Why do you want?
Why do you want this?
Yes.
Okay, you'll see this in the next step.
Okay.
Yeah, yeah.
What would compute that basis?
You can get a good approximation to this. Yeah. If you want the actual basis with like no slack here, then I don't know. But if you allow a little bit of slack, it's possible. Yeah. Any other questions?
So step 1 has not used the second property of U.
Exactly. So step 1 has used basically nothing. I mean, it's used the first property of U, but the first property of U you get just by scaling. Yeah.
So your one norm is I take the absolute values of all matrix elements and then sum them up?
Exactly, yeah.
I see.
OK, cool. So what is step 2, the more interesting step? Well, we want to show a subspace embedding, right? So we care about the one norm of SUX for an arbitrary x. OK? Now, the one norm of SUX is at most the one norm, entry-wise, of the matrix SU times the infinity norm of x, right? Because for each row, each row is a dot product. The row dot product is upper bounded by the one norm of the row times the max entry in x. And so I'm just doing that for all the rows. Yeah? OK. But what do we know about the entry-wise one norm of SU? Well, we just bounded it in step 1. So I can replace the one norm of SU with order RD log RD. Yeah? And the second thing, the infinity norm of x, that's at most the 1 norm of ux. That's where we use the second property. Yeah, question?
This ux is really the old ax. I mean, you mean to write uy here somewhere.
Oh, yeah, I mean, so I care about a subspace embedding. So I'm going to preserve the norms of everything in the subspace. So I can choose whatever basis I want.
Right.
Yeah.
But you've written ax in the basis u.
Yeah.
All
so
I'm saying is the x is overused.
Yeah. I see. Yeah. Okay. Yeah. You can think of ax as uy.
uy.
Yeah.
That's fine.
Do people see this step? So all it's using is, so it's sort of using a global event. You're saying the 1 norm of the matrix SU, this small matrix, is order RD log RD. And then you're using this nice property in the basis to say that the 1 norm of SUX is at most the 1 norm of UX. And here's where you use the second property. That's the whole thing. That's the whole argument for a subspace embedding. Right? We saw in the previous slide, that you don't shrink, the 1 norm doesn't shrink with very high probability. And that was so high you could union bound over a net. And this says the 1 norm doesn't grow that much. Okay? Okay, cool. So that's the proof of a subspace embedding for L1. But now you might ask all the questions that we asked for L2. It's very slow to compute a dense matrix of Cauchys times a vector or times a matrix. So Michael has a nice work using sparse Cauchy embeddings. So what if we try to adapt count sketch for L2 to L1? So what we do is we take one of these sparse matrices again. In count sketch, in each column you had a single non-zero entry, which was a random sign. But let's replace that random sign with a random Cauchy. Okay? So that's all that's happening here. And what they proved is if you choose a number of rows here which grows as roughly d to the 5th, then you get a subspace embedding with this kind of distortion. So the distortion is the 1 norm of SAX is at most d log d, the 1 norm of AX, and at least 1 over d squared log squared d, the 1 norm of AX. So ignoring log factors, this gives a d cubed distortion. Right? I shrink by at most 1 d squared, and I grow by at most d. OK, but it's very fast. I can compute S times A in input sparsity, number of non-zero entries of A time. OK, but there are a lot of natural questions here. And so let me now get to this work. The first natural question here is d log d distortion necessary for L1 oblivious subspace embeddings? Or can we achieve 1 plus epsilon distortion like we could for L2? So I want to mention if your subspace embedding is non-oblivious, then you can do a special kind of sampling called Lewis weight sampling that Richard and Michael Cohen had a nice paper on. So these are special sampling properties that depend on your matrix. Okay? But I want to ask for oblivious sketching matrices, which have applications to things like distributed computing and streaming. Can I get 1 plus epsilon distortion? Another question is, OK, suppose that maybe we couldn't. Suppose we can't achieve this. Can we at least have sparse L1 oblivious subspace embeddings with the same number of rows and distortion that we got in the dense case? Right? Can we get a number of rows which is d log d and d log d distortion, but have a very sparse sketching matrix? And more generally, can we have this kind of trade-off in Osnap that we had for Osnap between sparsity and number of rows? So these are the two driving questions of this work. Any questions? OK. So our first main result is a negative result. We show that for any p, not just p equals 1, for any p between 1 and 2, strictly less than 2, any LP oblivious subspace embedding with r rows has to incur this amount of distortion. Okay, so let's try to parse this messy-looking quantity. So the distortion is 1 divided by 1 over d to the 1 over p, log to the 2 over p r. Remember, r is the number of rows, plus r over n to the 1 over p minus 1/2. Okay, so what does this funny thing look like? So first of all, when r equals n, the number of rows in your sketching matrix is the same as the original dimension n. You can always choose the identity matrix and have no distortion. So you should get no lower bound here. And indeed, if I put r equals n here, this term becomes 1. Okay, and so 1 over 1 plus something, at most 1, I get no lower bound. Also, we know that when p equals 2, there is a nice oblivious subspace embedding that we already talked about. So the lower bound should also break down as p approaches 2. And indeed it does, because this exponent is 1 over p minus 1/2. If p is 2, the exponent is 0. R over n to the 0 is 1. And I also get no lower bound. Okay? As I would expect. Okay, so this is just explaining some of these terms. What is a typical use case of this theorem? So when p equals 1, let's see what we get. Typically, you want a number of rows r that is a small polynomial in the dimension d that you're solving regression on, right? So let's say r is polynomial in d. And you want to do dimensionality reduction, so let's say your original dimension n is much larger than your sketch dimension r. So this r over n term I'm just going to ignore. It's very small, okay? Then this log to the 2 over p, p is 1, of r, this is theta of log squared d, right? Because r is poly d. And this 1 over d to the 1, when I bring it to the numerator, I get a d over log squared d lower bound for p equals 1. Okay? And if you remember this dense Cauchy matrix, it gave us a subspace embedding which had d log d distortion. So the lower bound is optimal up to a log cube d factor, okay, a polylog factor. Question, yeah?
So when you write this distortion, is this, like, should I think of it as 1 plus epsilon or epsilon? This is 1 plus epsilon. So it's
No, so we can't get 1 plus epsilon. I mean, this whole thing is 1 plus epsilon.
No, I think
but
he means 1 plus.
Yeah, yeah.
It says 1 plus epsilon.
Yeah.
The whole factor.
right.
So it's the whole factor.
So if
and
it's like 1, then if the lower bound is 1, then it's useless.
yeah, exactly.
Right, okay.
Yeah. And it becomes 1 if r equals n or p equals 2. Yeah. Yeah. And so we're getting a lower bound in a typical use case of something like d over log squared d. It's much higher than the 1 plus epsilon that was possible for L2. Yeah. Questions? Okay. So here's the proof. So if we want to prove a
What's the saying? So
Yeah.
This, the Lewis thing is the refinement of the descriptive thing, right? That you get relative on L1 with this.
Yeah. Yeah.
So if you look at it, or if you do an oblivious thing and then do a second step where you look at the residual, which means you're looking at it, then you get 1 plus epsilon.
Yeah. So if
And
you
this is
actually
saying you can't, that there doesn't exist, or you can't find it sort of algorithmically. What's the lower bound?
This is for oblivious subspace embeddings, okay? So there's some matrix A. I sample my subspace embedding S from a distribution that does not look at A. And then I compute S times A. And then I ask, what's the distortion?
So for any distribution, that's
Yeah, there's no distribution that will give me better than d log d, I mean, about d distortion.
So there exists embeddings, but if you query the embeddings in this distributional way, then you won't, because there's a failure probability.
Yeah, so this
in
is like the
sample
difference between
distribution.
leverage scores and random Gaussian matrices, right? So leverage scores are data dependent. They look at the matrix, you figure out the right distribution.
No, I understand
Yeah.
that. What I'm saying is
That's the difference here for L1. Yeah.
there exists oblivious embeddings, but you can't find them in this model where you're doing sort of an oblivious, where you do an oblivious query of the distribution.
Yeah. So there's no distribution for which, with say constant probability, I sample a matrix from that distribution, I apply it to my input matrix, and I get a good less than D distortion.
Okay, good. So it's sort of
Yeah.
a quasi-algorithmic result. So there may be good things, oblivious things buried there, but you can't find them with more than exponentially unlikely or something.
That's right. Yeah.
So
I guess it's.
I mean, there's some, like super tiny probability that all my Cauchys, I sample them and they equal the Lewis weights. Right? I mean, but that's not going to happen, right? It's like
But the difference is oblivious just means that the probability that S works for all A is small or big, whereas non-oblivious means for every probability that S works for that A.
Yeah. So S depends on A
Yeah.
in the non-oblivious
So
case.
really, I guess the statement is the statement that for any oblivious distribution, there exists a matrix for which the distortion will be at least this much, or is that, or does it say that for?
I mean, for any S, I can always find like a really bad A, right, just by putting it in the kernel. So the statement
That's different.
is stronger than that, right? It's saying that like there's no distribution on matrices, so that for any fixed A, I sample from that distribution, I apply S to A, and I get a subspace embedding with, say, probability 2/3 over my choice of sampling matrix. So it's not like, it's not the statement that, for any sampling matrix, I can find a bad A.
No, but I meant
Yeah.
for any sampling distribution.
Okay.
Are you saying that you can find A, right, for any sampling distribution?
Yeah, I'm saying that, for any sampling distribution, it won't have the property that for all A if you sample from it, so therefore there exists an A which is bad for that distribution. Yeah.
Could you say that maybe, I mean, I guess.
I will give you an A. Yeah. Any other questions? Okay. Let's do the proof. Okay, and this is getting back to the order of quantifiers that you guys are talking about. So I want to prove there's no distribution, so that for any fixed A, I have a subspace embedding for A with good probability over my distribution. So a common technique in lower bounds is Yao's minimax principle. What you can instead do is show a lower bound for the following process. You can construct a distribution over inputs A, n by D input matrices A, and show for any fixed sketching matrix S, the lower bound holds. Okay, so this is a standard technique that, like a lower bound for randomized algorithms, you can instead give a distributional lower bound for a fixed deterministic algorithm, right? Which is
Just roll some columns.
Yeah, exactly. Yeah. Everyone's okay? Okay. Okay, so a natural question is, so I want to construct a distribution over matrices A. What should I choose? Here's the picture. What are the bad matrices A? And it's good to understand these because, maybe you can get L1 subspace embeddings, good algorithms, for other kinds of A that are far from this kind of pathological case. So you can view this A as a gradual mixture from L2 to L1. Let me say what this means. So A is an n by D matrix. We're going to have log n over D blocks. Okay, block 1, block 2, log n over D. In each block, we're going to have the same number of vectors, right? So we have D total columns. So each block has D over log n over D. Think of it as roughly D columns. And in the first block, the vectors are going to be n over D sparse. So that means they have n over D non-zero entries chosen uniformly at random. And on those n over D entries, they're random Gaussians. Okay, that's the first block. The second block is I'm going to have n over 2D sparse vectors. Okay, so now the sparsity has gone down a little bit. Instead of n over D, it's n over 2D. The third block, I'm going to have n over 4D sparse vectors. And in general, the ith block, the sparsity of the vectors is n over D times 1 over 2 to the I. Okay, so in the last block log n over d, I have 1 sparse vectors. They're just standard unit vectors, right? I mean, scaled by Gaussian. So like I choose, in this last block, I choose a random location, I put a Gaussian there. Do the same thing for each of the columns. Okay, so the sparsity is at every scale here. Is that clear? And finally, I have 1 fully random Gaussian vector. That's the whole matrix A. Questions? Okay, so why might we want to choose this matrix? Well, okay, why does it work? Any L1, yeah, question?
So the columns that don't have these sparse vectors, what are in those columns then?
Yeah, that's perfect.
Yeah, I mean, I have d columns, and what I have is log n over d blocks. And in the ith block, I have d over log n over d vectors that have the appropriate sparsity size for that block, namely n over d over 2 to the I.
Oh, so the sparsity of the vectors changes
Yeah.
between
Yeah.
the block?
Yeah.
Got it.
Yeah, so they're starting off with like roughly n over d non-zero entries, ending up with 1 non-zero entry. And then finally, I have a Gaussian vector. Clear? Okay. Okay, why does this work? Well, any L1 oblivious subspace embedding with distortion kappa satisfies the 1 norm of SAX is at most the 1 norm of AX is at least 1 over kappa the 1 norm of AX. Okay, I'm just writing it this way. I can scale by kappa if you want to write it in a different way. Okay. What is the implication of the ith block? Like, why do we want these sparse vectors? So let's look at each vector in the ith block. Well, it has n over d divided by 2 to the I non-zero entries, right? That's how we constructed it. And all those non-zero entries are standard Gaussians. Okay, so the L1 norm is going to be n over d over 2 to the I up to a constant factor with very high probability, right? I take that number of Gaussians, so I should get that L1 norm.
To be Cauchys rather than Gaussian? I'm confused because we have the 1 norm, right?
I mean, we're doing a lower bound. I want them to be Gaussians.
I think you just take all the positive ones. I mean, she wants to know how you get 1 norm. You take all the positive signed Gaussians, add them up, you get this one.
Oh, why is the 1 norm of a vector of Gaussians the
That's fine. I just thought, you know, we related the 1 norm to Cauchys before. And now I'm wondering why all of a sudden we have Gaussians when we're doing a 1 norm.
you'll see like the role of the last Gaussian vector in a moment. Yeah. Hold the question for just 1 second. Yeah. Okay. So so here's the critical observation. So we have a fixed matrix S, right? We're proving a lower bound for it. If there are more than 2 to the I, we're looking at the ith block, 2 to the I polylog n columns of S that have L1 norm at least n over d over 2 to the I, then with good probability, some vector in the ith block, remember we have about d vectors in the ith block, formally d over log n over d. Some vector in the ith block will find it. What does it mean to find it? Well, the vector has, in the ith block, has n over d over 2 to the I non-zero entries, right? Now, what I mean by find it is I look at the columns of S, and if one of those non-zero entries indexes one of those columns of S, then I found it. Right? I mean, I have some sparse vector, and I'm asking, which columns of S get touched by that sparse vector. So I have n over d over 2 to the I non-zeros, and I suppose I had 2 to the I columns with a certain 1 norm, then with probability about 1 over d, I would touch it. I would touch that column with my non-zero entry. But I have d columns, or d over log n over d columns in the ith block. So if I have 1 over d probability of touching it for 1 column, then I have about constant probability for touching it if I have d columns. right? I mean, each one has probability about 1 over d, and I'm sampling d times. And if I touch it, then I'm in really bad shape. Why? Because if I touch one of those columns with my non-zero entry, what is s times the vector? Well, it's the sum of the columns it touches scaled by Gaussians. And if I touch a column with L1 norm at least n over d over 2 to the I, then I might touch more than one. I'm going to add them up. But with good probability, the 1 norm of that sum is going to be at least the 1 norm of one of those columns I touched. Right? I'm adding up a bunch of columns. I mean, likely I'm only going to touch one of them. I might touch more than one. But the point is, when I add up these columns, if each one has 1 norm at least n over d over 2 to the I, and I'm adding them up, then I'm likely to have L1 norm at least n over d over 2 to the I. Right? But that's a problem because in the ith block, the vector has 1 norm n over d over 2 to the I. And this subspace embedding says, oh, well, I can't, the length of SAX can't be larger than the length of AX. Yeah.
So, are you talking about the rows of S touching that rather than columns?
No, right. So like, yeah, I wish there's a board here. Yeah. So here's S, right?
Right.
And I have columns in S, and I'm applying it to a vector, right? So like I look at the ith entry in that vector that's non-zero, say. When I do this product, that index is the ith column of S, right?
Right.
So I'm adding up like a subset of columns of S corresponding to the non-zeros of my input vector. And I'm scaling them by the non-zero values, which are Gaussians. Does that make sense?
Yeah, and the Gaussians have signs.
There's Gaussians, yeah. I mean, there's like standard Gaussians.
Okay, there may be cancellations.
There could be cancellations, but all I'm saying is with constant probability, if I touch one column with large L1 norm, and I add it up, maybe I touch two columns, right? But still, with constant probability, the L1 norm of the sum is going to be larger than the L1 norm of one of them, right? Like the sign, like one of the signs is good.
That's true. The variance just increases. Okay, yeah.
Yeah. So basically, if I touch one of them with constant probability, I'm in trouble because one of them, we're saying, I can't have, each one of them has L1 norm n over d over 2 to the I. If I touch one of them and my input is only L1 norm n over d over 2 to the I violate this subspace embedding condition. So this says there can be at most roughly 2 to the I columns in S with L1 norm about n over d over 2 to the I. Okay, so let's step back and see what we learned. Otherwise this subspace embedding condition is violated, like I said. What did we learn? We learned something about the sketching matrix S. If it's a good subspace embedding, let's look at its columns. And let's look at the L1 norm of its columns. The L1 norm, it looks like a Cauchy distribution, right? We can't have more than 2 to the I columns with L1 norm more than n over d over 2 to the I. We've characterized the distribution of L1 norms of columns of S. Right? I mean, this is exactly what you would get if S were a Cauchy matrix and you scaled by 1 over d. Okay, so you're basically saying you can't have, what this is saying is there's at most one column with L1 norm at least n over d. At most 2 columns with L1 norm at least n over 2d. At most 4 columns and so on. Yeah? So I get the whole histogram of S. Okay, yeah. Oh, I should wrap up so you guys can actually take the bus. Yeah. Yeah.
Leave in about 4 minutes.
Oh, it's okay. Hard constraint, right? Okay. Yeah. Let me just give.
Otherwise, everyone's allowed to leave in about a minute.
Yeah. Let me just give you the punchline. Like, what was the point of all this? And it's just one more slide. This is just a picture of what we just showed. We have one column with L1 norm n over d, 2 columns with L1 norm n over 2d, and so on. And we have a bunch of other columns that have L1 norm at most a constant. Okay, here's the final thing. Remember, the last column in A is a full Gaussian vector, IID Gaussians. What is its 1 norm? It's n, right? About n. Okay. But for a full Gaussian vector G, what's going to happen when I apply S to it, where S has this histogram of 1 norms on its columns? Well, I have one column of L1 norm n over d. So maybe I'll get that one, I'll get n over d. I have 2 columns of L1 norm n over 2d. Maybe I'll get both of them. In the best case, maybe they all add up. They all have the right signs. In a very wishful, hopeful case, I only have log n over d blocks. Each block contributes n over d plus n over 2d times 2, that's n over d, plus n over 4d times 4, that's n over d. Each block is contributing n over d. So my 1 norm of SG is going to be about n over d. And I also have all these very light columns that have L1 norm 1. But if I multiply a Gaussian vector times vectors that have L1 norm 1, I'm going to get something about like square root n. So those tiny L1 norm columns don't do anything. And the large ones give you at most n over d. But what we know is that like the L1 norm of the Gaussian vector is n. And we just said that the sketch gives it L1 norm n over d, which therefore implies that the distortion of the embedding is at least d. That's the whole proof. Questions? OK, so let me just wrap up. This was the lower bound. And there's also an upper bound in this paper if you're interested. So we do get sparse L1's oblivious subspace embeddings, which match the same parameters as the dense case. And I'll just stop here. Yeah.